Hi, I'm here in Toronto. Earlier today, I gave this presentation at the Acceleration Consortium's Accelerate conference. Had a wonderful time there. Very grateful for the privilege to have been invited to come and speak here in Toronto at the University of Toronto, and meeting some phenomenal people here. And I figured I'd like to record this presentation, uh, make it available, and if I didn't do it now, it probably wouldn't happen. So here we are. I'm presenting on a minimal working example for self-driving laboratories. Uh, this is what we call the SDL Demo, a hello world for autonomous research labs. So picture all the automation and the AI, the different components you get in a Tesla that allows a Tesla to be self-driving, make decisions in this feedback loop, and bring those aspects, those principles, into a chemistry lab where people might normally be mixing things by hand and running these experiments manually and choosing deliberately every single experiment that they'll run next, maybe in a grid fashion or a design of experiments fashion, and transitioning that over to something where robots can handle the tasks involved, some of the more menial tasks, and where much of the decision making on the nitty gritty stuff of, okay, what exactly is the next experiment I should run to get the most information? That can also be relegated to an AI and free up more time for the researcher to do these higher level tasks like data analysis and designing the experiments, the search bounds, the different variables that will be looked at. And so what we're going over here is this minimal working example for it. And I'd like to thank the NSF for funding. This isn't possible without some of the funding from different grants, and also acknowledge the many useful discussions and suggestions that I've received from some phenomenal individuals helping me out, troubleshooting, and helping me to avoid some roadblocks with this project. So there are many excellent low-cost platforms for fully autonomous demos, dating back to as early as 2014, maybe some before that, and with many recent examples even this year. Now, these examples range from oil droplet experiments using a 3D printer, looking at how oil droplets coalesce, to chemical reactions, color matching and mixing, as well as pH sensing and optimizing a 3D print, optimizing the parameters there. For wider adoption, though, there needs to be a demo that's cheaper and easier to set up. If you take a look at the existing demos, you're looking at least a few $100s for most of these. Now, that might not be so bad in an educational setting. However, many of them also require custom parts. And so this increases the setup time required. It increases the expertise required to set up one of these demos from scratch. And what we're proposing here is a platform that can cost less than $100. The iterations can be done very rapidly in 1 or 2 seconds. No custom parts are needed. And there are also no robotic axes, which can be seen as both a limitation and a strength. Strength in that it dramatically reduces the cost necessary to make this simple working example, but it also removes some of the more chemistry and material science heavy concepts and domain knowledge that can come from this, and so that's something we'll talk about towards the end of the talk as well. So, what is a minimal working example? This is a term that comes from programming. If you've ever asked a question, had a problem with code, and you go to someone and you say, "Help me out," what do you provide them? Well, what the developer would really like to hear and to have is seeing a minimal working example. An example of the problem you're running into or something that you want to implement that uses as little code as possible while still producing the same problem, providing all parts needed to reproduce the problem in the question itself, and that you've tested this code you're about to provide to make sure it actually does reproduce the problem. And so this developer can come in, they can take a look at your code, they can plug it in on their own machine, test it out very quickly, reproduce the exact same error that you got, and very quickly drill down to the exact issue and help you out rapidly. And oftentimes, developers will ask for these minimal working examples because it dramatically reduces the burden on the developers to provide assistance with these. It allows them to do a lot more with their time in supporting the communities that they serve. Now, let's talk a little bit about what that might look like for a self-driving laboratory. And we propose that minimal means minimizing the cost, size, and setup while still being a self-driving laboratory. And that complete means you've provided software with documentation and a bill of materials with setup instructions. And for reproducible, meaning that you can benchmark this self-driving laboratory using a fixed configuration and verify that the results are expected. So you can run this, have someone else run this, and you'll get approximately the same results. And when we take a look at robotic arms, low-cost robotic arms, usually these are start out at least $100 worth of equipment, but you get a pretty high cost in terms of how long these take to set up. You could be looking at 20 or more hours to get one of these simple robotic arms working and functioning as you intended, or you can pay more, you know, 500 to 1,000 for some turnkey solutions, some things that work a little bit better out of the box, but you naturally have a higher price tag associated with those. Very similar story with 3D printers. The cost over the last decade has come down dramatically, making them a lot more accessible, a lot more open. The much lower cost printers still have a fair amount of setup time involved, as well as troubleshooting on the back end, leveling printer beds and installing new hardware, different troubleshooting. And similarly, you can get pre-built solutions and higher cost solutions that reduce some of that troubleshooting burden later on. Then we have peristaltic pumps. There were many of these used in the examples that I showed earlier, and these peristaltic pumps really start to come closer to the cost point that we'd be looking at for and needing for a demo like this. But we can actually go even cheaper as we move to signal and source using a light emitting diode or an LED, and using that in place of a material or matter. After all, light is a lot easier to move than matter. And while it doesn't have that chemistry and material science aspect, I'll show how we can retain many of the key aspects of a self-driving laboratory in the chemical and physical sciences in a way that can still teach important principles while just dramatically reducing that overall cost and some of the difficulty in setting these up. So let's delve a little bit into the task at hand. So you've got these two LEDs, these red, green, blue, or RGB LEDs. And on the left, you have this sort of purplish one, and on the right, you have this kind of pukish green one. And if you wanted to change the colors on the left, the individual red, green, blue values, to match the color that our eyes see, at least on the right, what would you do? If you had these knobs in front of you, you might just start turning them, and once you start getting something that looks a little bit green, you'll say, oh, okay, let me try to fine tune there. It's a very manual process, not necessarily reproducible, and you might get something that's only kind of close to what you see on the right, which that opens up the idea and the opportunity to use different optimization algorithms to very efficiently change your inputs, measure the outputs, and converge on the target solution that you were looking for, whether that's maximizing something or minimizing, in this case, minimizing the difference between what you're currently observing and what you want to observe. So this is the task, just this sort of simple light matching or color matching using light. And I mentioned before that the SDL demo retains key features. Some of these are sending commands, reading data, and the ability to optimize or close the loop in an optimization loop. So here we have this dimmable RGB LED. So 3 distinct LEDs, each with their own wavelengths, characteristic spectra and wavelengths. And so, blue is sitting around 470 nanometers, green at 528, red at 622 nanometers. And you can control the individual brightnesses of each of these LEDs using a microcontroller and sense the spectrum, or kind of the mixture of that light, using a low-cost sensor with 8 discrete wavelengths that it measures. You define some target spectrum, which could be completely arbitrary, and is really arbitrary for this demo. But you pick one, and you measure the difference between what you just measured and what your target is. And you can use that in a loop, possibly with some physics simulations integrated there, which we'll go into more detail a little bit later. And ask yourself the question, what method can I use to reach the target? And this is where some of those optimization algorithms come in. You could use something very simple, like making a grid of points and testing them out. You could do something a little bit more efficient, at least generally, where you randomly search for points in this space. Or you can use something even more advanced and typically more efficient, but a little bit more computationally costly, algorithms like genetic algorithms or Bayesian optimization, which is one that I'm very partial to. So then you close the loop, and you run this in cycles for however many iterations, 10, 50, 100 iterations, looking at how you converge on the target value, reducing that difference. So let's go a little bit into the parts here. So this was designed, and there are many other designs this could take on. There were no custom parts and no additional skills, such as soldering, involved with the setup, which translates to a low setup time, setup cost. And so you've got these two carts, one from Adafruit, totaling to about $40 US, and then some sculpting wire to help you position the sensor a certain distance away from and perpendicular to the LED. Just something you get from a hobby shop or Amazon, and maybe you have something else that would work just fine in its place. So here we have a working demo where we're able to send color commands and read the sensor data via, and don't get too scared by this, a web server hosted on the Raspberry Pi Pico. And while it can take a little bit of knowledge and getting used to if you're not familiar with web servers, I certainly wasn't before this project. Once it's ready, it's fairly easy to adapt into different applications. And this is one of the nuances of using a microcontroller instead of a single board computer that could run the full version of Python on a Linux operating system, or Ubuntu Linux, versus a microcontroller that in this case only has 2 megabytes of RAM to store. So you can't use a full programming language. You need something that's called MicroPython to be able to make this work with the Pico wireless. And you can, on the left here, you can see how you can enter in values for the red, green, and blue, send the command, and then measure the latest sensor data here. And next, we have that the SDL demo provides an opportunity to illustrate efficiencies of common algorithms. So this points out one of its ways it can be a teaching tool, while it may not be particularly interesting from an optimization benchmarking perspective. So in the blue, we have a grid search method, in the red, a random search, and then in green, Bayesian optimization. And we see that, as one would expect, based on trying these algorithms on different problems, that grid search is the least efficient, random search comes next, second place, and that Bayesian optimization is very efficient, quickly overtakes the random search by the 10th iteration or so, and drops the error between your target spectrum and the spectra that you're measuring very quickly here. And we can take a look at what each of these searches look like qualitatively. So with the grid search, you can see that it's starting from 0 power and then increasing the brightness for a fixed color and then moving on to a somewhat different color and it repeats that. Whereas with random search, you'll see that it's picking random intensities, random colors. As the name implies, you're getting just a random search, which can be fairly efficient and generally more efficient than grid search. And last, we have a Bayesian optimization algorithm, which there's some great resources for understanding Bayesian optimization on Towards Data Science, and I encourage you to look at those if you're not familiar. What's happening here is that each trial is taking longer in between iterations, and that's because internally within the Bayesian optimizer, it's fitting a model and it's trying to compute based on that model where the next best place to search is. Essentially, what next experiment will give me the most information or help me to most quickly reach the true minimum error in this case. And so here we have the comparison of 3 optimization algorithms. And earlier I mentioned that this is compatible with running simulations, something that's very common in chemistry and material science. On the left here you see a diamond sintering anvil. There aren't very many of these in the world. They're very expensive. We're looking at on the order of tens of millions of dollars for one of these, and it can take a very long time to prepare samples and run these experiments. Very expensive process. And alternatively, we can run simulations that can get us similar data for the bulk modulus. And with this, you can use some common software packages like VASP and wrappers for it that give you pre-built workflows, like the ones that are used for the materials project. You have some input structure that you need to have or determine, and you can extract the bulk modulus from these simulated values of compressing the microstructure and looking at how that changes the volume. So next we have an example of a simulation involving the Sdl Demo. Now this, on the left here, we have a snapshot from an LED data sheet, and you can see the blue, green, and red spectra for a particular LED, and we can use a tool like Webplot Digitizer, which we've liked using, to extract the individual data points from each of those curves. From there, we interpolate. We have an interpolator for red, an interpolator for green, and an interpolator for blue, and later on we can sum different ratios of that interpolated curve, in this case just a linear interpolation, to arrive at a new simulated light mixture. Now this isn't just yet to the point where we have the same kind of data we receive from the sensor, but we're getting closer there. So from here, we can take a look just sampling this simulated spectrum at the same locations that the sensor would be measuring at. And you can see 2 kind of visualizations of that, each of the colors being sampled there, as well as this bar chart, sort of a histogram of intensity versus wavelength there. And we created a class that allows you to very easily switch from experimental to simulation mode, and so that makes it a little bit easier to swap things out in your code. You can just switch an argument from true to false in order to switch between simulation and experiment for this. And we've prepared a series of notebooks that illustrate various self-driving laboratory troubleshooting principles in a very low-risk setting here. So you can start out with just flashing the LED, reading some sensor data, then reading some sensor data while flashing the LED, then introducing a basic search algorithm, and moving on from there, implementing the simulator class and testing it, kind of taking a look at the basic physics involved with those decisions, and finishing off with this comparison of the different search methods. And more notebooks to come. If you have any that you'd like to see, please let me know, and be happy to see if it's something I can implement and get back to you on. So here, I'm going to talk about how this demo is both modular, which I described a little bit earlier, and extensible. So with the appropriate add-ins, you could convert this to a chemistry-based color matcher, similar to the ones that we saw at the very beginning with these mixture of molecules to match a particular color. You can use this, you can have sort of some power hardware that allows you to control, so a shield that allows you to control a peristaltic pump, connect those to the peristaltic pumps to your dyes or your sources of colors, and then use an increased integration time with the light sensor to be able to detect what the final color of your solution is. You could also add a pH sensor here, a low-cost pH sensor using one of the nice Grove ports on the MakerPi Pico base. And so this way, you simply need to plug in the appropriate cord to the different ports and use the corresponding packages or some of their demo code to read the data that you need. And a similar approach can be used for more advanced automation tasks. You can picture something using computer vision with these 3D position trackers or April tag fiducial marks, or maybe even putting a low-cost robotic arm on top of a mobile robot and having that move around and pick some things up and demonstrating a basic chemistry or material science task at hand, maybe mixing some solids or liquids together and testing various properties there. And so you can use some of the same equipment here, but in an extended way using these different sort of add-on modules. If you have other ideas, please let us know. Next, I want to talk a little bit more about the design decision for the microcontroller. Now, single board computers reduce the amount of custom microcontroller that you need. Like I said, only so much can fit onto this 2 megabytes of RAM on the Pico wireless, which is actually kind of a lot as far as microcontrollers go. And so you need something like MicroPython. Whereas many Raspberry Pi single board computers can run 64-bit Ubuntu, a Linux operating system. However, it's been very difficult to procure some of these single board computers due to the chip shortage. So we have the Raspberry Pi 02W, 512 megabytes, a very popular one for Internet of Things, wireless applications, nearly impossible to get right now. You have the Raspberry Pi 4B, which comes in different RAMs, up to 8 gigabytes of RAM, which is pretty nice. However, also difficult to get. And then you have a more expensive module, something that starts around $100 for a kit, the Raspberry Pi 400, which has essentially a Raspberry Pi 4B 4 gigabyte RAM module embedded into it, essentially, which is you're more likely to find available, but it kind of pushes us past that price point of less than $100 that we're aiming for. And I made designs for each of these and slowly progressed from some of the more expensive designs or the ones using some of these single board computers, and eventually nailed it down to a Pico W solution based on just the availability of the hardware. And this demo can be used for both education and low-cost prototyping. It's more accessible for teaching due to its low cost, small footprint, and easy setup. The demo can also be adapted to suit the needs of a particular course. So you could have a focus on simulations versus experiment and the presence of noise and bias and uncertainty measures. You could compare basic optimization algorithms like I showed before, and you could even get into some more advanced topics like multi-objective optimization, multi-fidelity optimization, where you're incorporating uh, multiple qualities of your data, like experiment being more of the ground truth that you're looking for, and then simulations being lower fidelity, but much less expensive to run, and so forth. And this can also be, I mentioned the prototyping, this can be a stepping stone for showing some dummy methods or dummy results for you to include in a grant proposal. And you could look at some different topics like distributed experimentation, where you put a network of robots together, performing experiments with some central brain, sending commands out. You can have formulation-based optimizations with some cheap characterization hardware that after you get the grant proposal, you replace with much more expensive real-world task characterization equipment. And you could look at advanced automation tasks like doing liquid and solid handling and computer vision, using some of those extensions that I mentioned earlier, and kind of troubleshoot and prepare the way for doing that for a real critical materials task for improving society. And next, this low-cost prototyping can help you guide design decisions for the real application. And that's especially applicable for first-time grant proposals. If you've never set up a self-driving laboratory before, getting this hands-on experience can really help you to flesh out the idea, figure out what will or might not work. And that modularity really helps with troubleshooting complex systems where you say, okay, can I turn on the LED? Can I read data from the sensor? Because as these systems get more and more complex, they also become exponentially harder, or at least combinatorically harder to troubleshoot, because the number of ways that the system could fail is increasing dramatically the more components there. So that modularity really helps to reduce the time needed to troubleshoot some of these systems. And finally, a few comments on the limitations of this and the design considerations that went into this. So like I said, there's no chemistry and there's no material science, which is both a strength and a weakness. It's simple to set up. There's some basic physics involved, but no chemistry or math side principles. So there's still a need for a minimal working example for materials acceleration platforms, which is essentially a self-driving laboratory applied to the discovery of new materials or getting, breakthroughs in our understanding of these materials and so forth. And there's also the argument that this setup could be a single LED and a single brightness sensor. However, there weren't really any existing solutions that just had a board with a single LED. We could use a breadboard, but that increases the chance of initial failure and frustration, and is less aesthetic. Now we could use a custom printed circuit board, but that is a higher setup cost, harder for people to repeat and source, and there's a cost associated with these custom prototypes. And last, the optimization task is quite simple. They're linear responses except for noise, and the superposition principle applies where you can essentially just stack the spectra on top of each other and you get the final mixture of light. Since we're using very basic setups here, not really anything where light is canceling each other out, at least in any measurable way or noticeable way here. So it's not really as interesting from an optimization benchmarking perspective. You could make a custom printed circuit board with 10 or more distinct wavelengths, carefully selected. That would be more interesting, but it's still a linear problem. And so that's just one of the drawbacks of this demo, but it was also the intention and the purpose to keep this as simple and as minimal as possible while still retaining the key features that we wanted. And for alternative benchmarking frameworks, you could look into something like Olympus or by the Spurguzik group, very nice package there that Riley Hickman is working on. Some of the work we're doing with the optimization benchmark, this customizable benchmark where request a certain number of numerical parameters and a certain number of categorical parameters, and you have this complex task under the hood that starts to look more like a materials optimization problem, one where you're optimizing a formulation of things, and so it's subject to constraints as well, constraints that you specify. And there are other examples of optimization benchmarks and materials benchmarks that you can check out at the links below. So what have we gone over? We've taken a look at the SDL Demo, this Hello World style project for self-driving or autonomous research laboratories. We've seen that we can use this to do some basic comparisons of optimization algorithms. We've looked at how it's modular and extensible. We've taken a look at even running some simulations with it, and noted how this can be used for educational settings as well as low-cost prototyping settings. So how can you get involved with SDL Demo? First off, you can star or follow the repository on GitHub. This helps to get the word out, get more people aware of it, which is really important for these types of projects. You can order the bill of materials and try it out for yourself. And you can also sign up for infrequent updates, ask questions, or provide feedback at the link shown here. Thank you.